First one work I want to survey is joint with Eyal Lubetsky. It's a question we've been wondering about for some years, but this work was just completed this summer. So what is the setup? We have a deregular expander. So I told you a little about these expanders. What it means is that that there is a uniform spectral gap. Now, so if we look, lambda 2 here is not for the random walk, but it's for the adjacency matrix. So if you have the graph, you put a matrix, or you look at the adjacency matrix. So you have zeros for non-neighbors and ones for neighbors. And so this matrix has largest eigenvalue of d, the degree, rather than 1. And so expansion property means that the second largest eigenvalue is separated from d. Now, the larger this gap between lambda 2 and d, the better the expansion. And the Alon-Bopana theorem tells you how good the expansion could be. So lambda 2, again, this is not for the Markov operator, but for the adjacency matrix. Lambda 2 is at least twice root d minus 1, minus a correction which goes to 0 as the graph grows. So motivated by this and by specific constructions, Lubotsky, Felix, Sarnak defined the graph to be Ramanujan if it's a connected deregular graph, and all eigenvalues except the extremal ones plus minus d. So you could have minus d if the graph is bipartite, but all other ones have to have absolute value less than 2 root d minus 1. So it's not at all clear that such graphs exist. We now know they exist for every d, but it's not clear. And the first constructions were in the case when d minus 1 is prime by LPS and Margulis. And the reason they called it Ramanujan is it used some number theoretic ideas related to Ramanujan's work. It's not that Ramanujan himself thought of these graphs. So this is some attempts to visualize these graphs. This is a graph with 12,000 vertices, so we don't see them all here. Now, these graphs have high girth. So if you look at the local picture around the vertex, it looks like a tree to some distance. But of course, it can't be a tree forever. It's a finite graph, and it's this one is this one is 6 regular. So okay. So the structure, the local structure near a vertex is very simple, but our goal is to understand what's happening here. This is the eigenvalues of Ramanujan graphs shown in 2 cases. So the Lubotsky, Felix, Sarnak graphs have a very high multiplicity of eigenvalues. And in the same picture, we're showing the spectral measure of another Ramanujan graph, which is a lift of, so the Peterson graph is a very classical graph on 10 vertices, which is Ramanujan. And you can do a random lift of that. I maybe won't go into that, but there's another way to build the graph, which is in general conjectured to be always Ramanujan with high probability. But in this case, we verified it's Ramanujan. So there is another graph pictured here with 10,000 vertices, and its spectral measure looked like this. So the spectral measures of these graphs could be quite different, but they're all confined to this interval between plus or minus 2 root d minus 1. So our theorem is that the simple random walk exhibits cutoff. I'll say what that means, but what it means in this case is that the mixing time, T mix of epsilon, minus this quantity T star of n, which is log n multiplied by d over d minus 2. This difference is of lower order. It's order root log n. And this bound is sharp in the sense that this difference, really is of that order. So where does this number come from? Well, it comes if you have a tree of n vertices, and it's deregular, what is the depth of that tree? Because it's deregular, every vertex has d minus 1 children. So the depth, if it's a regular tree with n vertices, the depth will be the log to the base d minus 1 of n. However, we said that our graph locally looks like a tree. However, our random walk here is not just moving forward in this tree. It's a simple random walk. What is the speed of simple random walk on a tree? So if we have a deregular tree, right, every vertex has d minus 1 children and 1 parent. We have some starting node. So our random walk goes forward with probability d minus 1 over d and backward with probability 1 over d. So the speed is going to be d minus 2 over d. So this means that if we're doing random walk on a deregular tree, but a finite tree with n vertices, then to reach the boundary of the tree, the time it will take the random walk is this. And what we're saying is, even though our graph is only approximated locally by a tree, still the time to reach the boundary of this tree is the mixing time of the walk. It's actually very easy from these considerations to see that the mixing time cannot be lower than this. And so this is a lower bound for the mixing time on any deregular graph. So this is as fast as you can mix asymptotically on any deregular graph, just from these kind of comparison to a tree. But Ramanujan graphs, the basic thing you can come away with is the Ramanujan graphs mix as fast as possible. Random walk mixes as fast as possible. Okay, maybe I'll skip this picture and come back to it later. And let me say that we looked at mixing time in total variation. One can look at mixing time in LP for every p. So that would be taking the density. You take the distribution at time t normalized by pi, compare that density to 1, which is the density of the stationary measure with respect to itself, and look at the LP norm. So if you take p equals 1, you will recover twice the total variation distance. But other p's are interesting. And it turns out that for all p's, Ramanujan graphs asymptotically optimize the LP mixing time on all deregular graphs. And this is a graph of how the LP mixing time behaves as a function of p and the size of the graph. So this is the L1 mixing time, and we have a sequence of p's here. The most useful usually are the L1, the L2, which is pictured here, and the L infinity, which is at the end. The key. This is a problem I told you we were thinking about for years, and why were we stuck for so long? One reason is that Ramanujan graphs, what you have is spectral information. How do you use spectral information? The natural way is to use L2, to calculate an L2, because the eigenfunctions are orthogonal and so on. And in the classical works on cutoff by Diaconis and co-authors, the method cutoff is proved is you prove a lower bound in L1 by showing some statistic, and then you prove an upper bound spectrally or using representation theory using L2, and then you show that these upper and lower bounds match, and so you get cutoff. This is what they did. These are non-trivial calculations because calculating the spectrum in something like random transpositions requires some representation theory, but this is the basic method, and Now, if you examine all these graphs that they proved cutoff, random transpositions, hypercube, and all of them, besides the size of the graph going to infinity, also the degree goes to infinity. And it turns out this is a crucial element, because what turns out is that in any d-regular graph where d is bounded, then the L2 mixing time cannot be the same as this, as the fastest L1 mixing time. So I told you the fastest L1 mixing time, which is achieved in the Ramanujan case, is this number. But it turns out that the L2 mixing time is always strictly bigger by some constant factor that's away from 1. So there is no chance to prove this is the true mixing time, and there's no chance to prove it by directly working in L2, because the mixing time in L2 is strictly bigger. But if you have spectral information, how do you use that for L1? It's much harder. So we're stuck on that. So the key tool is to use non-backtracking random walk, which has been used in the area for a while, but in analysis of Ramanujan graphs. But we didn't realize it's really essential for cutoff. So the trick is, it turns out that for non-backtracking random walks, the non-backtracking walk is like simple random walk, except you're not allowed to cross on the edge you just used. So you take a step, and then the next step is uniform among all edges emanating from where you are, except the edge you just used. So there's no backtracking. And if you have a regular graph, then there is an easy reduction from mixing properties of the non-backtracking walk to mixing properties of the walk. And there's also a spectral connection between the spectrum of the non-backtracking walk and the spectrum of the simple random walk. And we were aware of this connection, but because there is this equivalence, we thought, well, since there is an equivalence between the spectrum of these two processes, then it shouldn't yield any improvement. But it turns out that this equivalence does yield something more than you can get if you don't use it. So there's something more subtle than meets the eye in this equivalence. So formally, the non-backtracking walk is a Markov chain on the edges of the graph. So this matrix B is a adjacency matrix for directed edges, right? So we have a directed edge, and basically in the graph, this edge is adjacent to all the directed edges that come out of this node. That's what's written there formally. So this is no longer a symmetric matrix. It's not a reversible Markov chain. So one has to be more careful in using spectral methods, because the usual tools, orthogonality of eigenvalues are not, and real orthogonality of eigenfunctions and real eigenvalues are not directly available. Now there is a classical relation between the eigenvalues of B and the eigenvalues of A, and it's given by this quadratic equation. So for every eigenvalue lambda of A, there are two eigenvalues theta of B that are the two solutions of this quadratic equation. This was first realized using zeta functions of graphs by Hyman Bass. It can be derived in a more elementary way. And I said I won't, in this time, be able to give you the full proof, but I just want to say what are the elements in a proof. And the element is a refinement of this classical Bass equivalence to a full Jordan form of this non-backtracking walk. So there is this operator B, or the matrix B that corresponds to non-backtracking walk, and what Bass tells you are what are the eigenvalues of this matrix. So these are these thetas that correspond to the lambdas, and there are some trivial eigenvalues that are plus or minus 1s. In order to perform an analysis, we had to add to this the fact that the Jordan form of this matrix just consists of 2 by 2 blocks. The reason this is not obvious is that the eigenvalues, in the case we are considering, the eigenvalues of the simple random walk have high multiplicity. So if an eigenvalue has a large multiplicity, it's not then clear that when you go to the non-backtracking walk, you won't get large blocks in that Jordan form. But the blocks are all 2 by 2, and we can say exactly what is the extra element or the off-diagonal elements in absolute value. So in the Ramanujan case, all these absolute values are exactly d minus 2. It's kind of, since it's such a nice number, it's kind of amazing as far as we know that it has not been observed or proved before. Although if someone would have done this, looked at the Jordan forms, empirically you would have seen, because you get d minus 2. But it's just a fixed. So all these absolute values are all equal to d minus 2 in the Ramanujan case, and they can be computed also in the other cases. So once we have that, we can basically, we understand that. We understand also how the eigenfunctions of the non-backtracking walk arise from eigenfunctions of the simple random walk. So that allows us to do explicit calculations with the non-backtracking walk, and then finally derive the behavior of the simple random walk by a kind of reduction on the tree. So again, this is some picture attempting to show how the eigenvalues behave. So let's see. So in the Ramanujan case, all the eigenvalues of the non-backtracking walk, all the non-trivial ones, are on the boundary of this circle of radius root d minus 1. So they all have absolute value root d minus 1. They're complex, and they sit in pairs here. In the LPS, Lubowski-Phillips-Sana case, the high multiplicity means that these pairs have some kind of very discrete distribution, while in Ramanujan graphs arising from random constructions, it's much more smooth. And then, okay, and once you have this picture, then you can just calculate explicitly the L2 norm, and it turns out that for the non-backtracking walk, the L2 mixing and the L1 mixing happen at the same time. So what goes wrong with the simple random walk is that if you have a simple random walk, it can, since it can backtrack and since the degree is small, then the largest contribution to the L2 norm comes from the walk backtracking a lot near the, just near its starting point, it walks back and forth a lot. And this means that with high probability, it will be near its starting point, and this creates an explosion in the L2 norm. And kind of to overcome that, you have to really run the walk for a longer time. The non-backtracking walk removes this effect. It doesn't allow the walk to backtrack. And once you pass to that, then it turns out the L2 mixing and L1 mixing for the non-backtracking walk happen at the same time. So there's a very nice analysis of this equivalence of the how you derive the eigenfunctions for the walk from for the non-backtracking walk for the eigenfunctions for the walk itself. But I think I'll let you look at that in the paper, because I wanted to tell you one more thing before my time is up. But let me mention one kind of useful tool that helps simplify the analysis. So remember that B is a non-backtracking walk matrix, and it's not symmetric. Now the original matrix of the graph, adjacency matrix of the graph, is symmetric, but it's undefined on a different state space. So it is a useful observation done together with Russ Lyons. You can find it, for instance, in our book, is that if you take B, the non-backtracking matrix, it's invertible, and if you add D minus 1 times B inverse to B, then the resulting matrix is now a matrix still on the space of directed edges, but it is symmetric. So then you can, so for that matrix, you have a very simple picture. The eigenvalues are real, and the eigenfunctions are orthogonal. But it's easy to see, there's a spectral calculus that tells you how the eigenvalues of the original matrix, B, or not of the original, of B and of C are related. Because if for any eigenvalue theta of B, then theta plus D inverse theta inverse will be I'm sorry, theta plus d minus 1 times theta inverse will be an eigenvalue of C. So this allows another explanation of the Bass relation. All right, so that's all I want to say about this. I mean, the paper is on the archive and you can find more. And I want to switch in the last part to survey a different work on a cutoff for random graphs. Okay, so this is joint work with, again, with Eyal Lubetsky, but also Nathaniel Berestitsky and Alan Sly. So here we are considering random graphs instead of these deterministic graphs I was talking about. So it's useful to remember the basic structure theory of the Erdős-Renyi random graph. So you have G and P, every edge is there with probability P. There's a subcritical regime where the largest component is logarithmic, a critical regime where it's n to the 2/3, and a supercritical regime which we will concentrate on where the largest component is linear size. And we're interested in random walk on this largest component. Okay, so again, for P, which is lambda over n, where lambda is bigger than unfixed, the largest component is order n. So there is some constant that you can compute in terms of this lambda. And that's the case we focus on. So remember that mixing time is, this is the definition for worst case mixing time. Here we'll want to consider not just the worst case, but also the mixing time starting from a fixed vertex. Now the cutoff phenomenon is when the mixing time doesn't depend on epsilon, so what asymptotically. So we have a sequence of graphs. We have cutoff if T mix epsilon and the ratio of T mix epsilon and T mix epsilon prime goes to 1 as we go along the sequence. So this is the case, for instance, for the top two random shuffle we discussed, for random walk on the hypercube, for random transpositions. All of these examples have cutoff. On the other hand, simple random walk on the cycle doesn't have cutoff. So that's an important distinction, first made by Aldous and Diaconis in the 80s. So actually, no, they both have to be less than 1. So cutoff phenomenon actually requires that the T mix of epsilon and T mix of epsilon prime will be, the ratio will go to 1 even if epsilon is close to 1. So so as I mentioned, most of the early examples were of high degree graphs, Diaconis, Shashahani, Aldous. And I told you the classical examples of cutoff, classical example is the hypercube, and classical example without cutoff is the cycle, or any finite torus. And now we're going to look at what is mixing time on the largest component of the Erdős-Renyi random graph. Well, the worst case mixing time, I'm going to focus on the supercritical case. The critical case is also very interesting, but I won't discuss it today. So for the supercritical case, we said the largest component, so write P is 1 plus epsilon over n. The largest component is of size constant times n, and the mixing time, starting from worst state, is order log squared n. This was found in two papers, Fontoullakis, Reed, and independently Beniamini, Kozma, Wormald a little later. And it's easy to understand where log squared n comes as a lower bound, because the way the critical, so here's the picture of this graph, maybe have a bigger picture in the next slide. Yeah. So although it's linear side, it has these paths that go off the main body of length log n. So if you start at somewhere like this star, then you have this path of length log n, and you must cross it before you can mix, because most of the graph is on this side of the node. But how long does it take you to cross a path of length log n? Well, you're basically doing random walk on a path. It's log squared n. So this easily gives a lower bound of log squared n. So everybody knew this. The hard thing is to show that this is sharp, so that after you reach this main body, this huge collection of n vertices still doesn't take more than log squared n. Now, in the analysis of the random graph, an important object is the 2-core. So the 2-core is obtained by repeatedly removing the leaves from the graph. So if you see any leaves, any vertices of degree 1, remove them and iterate. When you remove all the leaves, what you're left with is a 2-core. So every vertex in the 2-core has degree at least 2. And however, even in the 2-core, the mixing time is still log squared n. The reason is that even the 2-core, so here this is part of the 2-core, and there is a path here. Inside the 2-core, there is a path of length log n. If you start in the middle of that path, you're still going to need log squared n in order to mix. However, so Fontoullakis Reed in their paper, they said, well, we know the mixing time is log squared n, even inside the 2-core, but it looks like this is due to starting at special vertices. Maybe if you don't start in one of these bottlenecks, then the mixing time can be lower order. So this is what they asked, and this is what we show, that starting from a typical vertex, we get a faster mixing time, order log n, and cutoff. So this is the result with Berestitsky, Lubetsky, and Sly, that the mixing time is log n times some constant with error which is approximately root log n. So we do have cutoff, and it's at a much faster time. It's root log n, but this is when we start not at worst vertex, but at a typical vertex. Say the vertex that had initially the label 1, assuming it is in the giant component. Now, I'll only be able to kind of sketch the idea here. I just have 15 minutes left, but let me at least make the statement clear. What are these constants in front? So V here is the speed of random walk on the Galton-Watson tree. Remember in the first lecture we had this kind of democratic procedure where we tried to determine the speed of random walk on a Galton-Watson tree. But this is something, so in old work with Russ Lyons and Robin P. Mantle from the 90s, we have a formula for the speed of random walk on a Galton-Watson tree. So if you look at the Erdős-Renyi random graph and look at the local picture near one node, a typical, so not the worst case node, but a typical node, then locally it looks like a Poisson Galton-Watson tree with mean 1 plus epsilon. So you have branching process where the offspring distribution is Poisson with parameter 1 plus epsilon. That's the local behavior around the vertex in the Erdős-Renyi graph. This has been known for a long time. And so the mixing behavior depends on the speed of random walk on this tree, but not just on the speed, also on the dimension of harmonic measure. So what is that about? If we have random walk on a regular tree, then when it, of course, when it hits the boundary of the tree, it will hit it uniformly. But if the tree itself is not regular, like if we have a tree coming from a branching process, consider this branching process, maybe I'll do a different example. Consider a branching process which has 2 or 3 children equally likely. Okay, so that's a good example. So the offspring distribution is 2 or 3 equally likely. How many vertices do you have at level k? Suppose I look at level k of the tree. Approximately how many vertices do I have in this tree? Yes? The mean to the power k. The mean here is 2.5, so 2.5 to the k. Right? But if I could run random walk on this and see where the random walk ends up, it doesn't charge 2.5 to the k vertices. Strictly smaller so there is some number less than the mean, m minus epsilon, where the random walk concentrates on this m minus epsilon to the k vertices. And so this was, again, in work with Lyons and Pimentel of, it's called Ergodic Theory and Galton-Watson Trees from 95. And let me just explain the idea for that in a much simpler case of a non-backtracking walk. So suppose I consider a non-backtracking walk on such a tree and ask, so non-backtracking walk is much easier to analyze than the simple random walk on these trees. But it still has this kind of dimension drop for harmonic measure property. So look at non-backtracking walk here and ask how many vertices does it hit on level k. So to understand that for the non-backtracking walk is easy. If you look at it, the non-backtracking walk, it's just choosing blindly a path. So along the non-backtracking walk, half the vertices will have 2 children and half will have 3 children. So if I look at a typical vertex for the non-backtracking walk, what is the measure that is assigned to it by that same walk? It's going, what is the probability we will end there? It's 1/2 to the k times k over 2 times 1/3 to the k over 2, approximately. Because about k over 2 of the vertices have, so there is some square root k correction to that, but this is, so about k over 2 of the vertices have 2 children, k over 2 have 3. So if I ask what is the probability I land at a typical vertex here, it's going to be 1/2 to the k over 2 times 1/3 to the k over 2, which is 1 over square root 6 to the k. And what that implies is that the harmonic measure for the non-backtracking walk, the hitting measure for the non-backtracking walk, is supported on about root 6 to the k vertices. And root 6 is strictly less than 2.5. So there is a set strictly less than the mean to the k, which supports the hitting measure of the random walk. And in fact, you can show that not just the hitting measure, but you can find a subtree of this tree of growth root 6. So there is a subtree here where for every j, the size of the tree is asymptotic to root 6 to the j. And with high probability, the random walk is confined to that subtree. Now, a similar phenomenon happens for the simple random walk, but it's much less simple to prove it than for the non-backtracking walk, because we don't have the simple random walk. It goes, but then it comes back, and that depends on the degrees. So that requires a whole kind of theory to understand. But luckily, that theory exists. So the analysis of the Erdős-Renyi graph depends on a kind of the composition of the giant component, which I don't have time to go into, but there's a reference in the paper, so I'll have to skip that. And just, I want to compare random walk on the irregular graphs to random walk on regular graphs. So I told you before about random walks on Ramanujan graphs. Actually, an object that was analyzed a bit earlier is random walks on random regular graphs. Turns out these are easier to analyze than general Ramanujan graphs. So G and D is uniformly chosen d-regular end vertex graph. So, okay, and maybe I'll go to here. So Duret in 2007, and I also conjecture that independently, that the mixing time of simple random walk on the random 3 regular graph is with high probability 3 log base 2 of n. So remember, this is this formula, d over d minus 2 times log d minus 1 of n. So he conjectured that this is the mixing time on the random d regular graph. And this was proved by Lubetsky and Sly in 2010. And their method used the non-backtracking walk to do that. Okay, so maybe I'll want to emphasize this picture. So in the regular case, in the random regular case, and also in the Ramanujan case, what happens is that the mixing time happens exactly when the random walk reaches the diameter or reaches most vertices of the graph. So you have, as we said, it takes time, say in the 3 regular graph, it takes time 3 log base 2 of n to reach most vertices of the graph. Before that, you have no chance, even on the regular tree, to reach most vertices. And that is the mixing time. In the irregular case, the mixing time is strictly bigger than that. So even if you take into account the speed of the walk and ask how long till this walk reaches the diameter of the graph, that's not long enough to mix. So this is related, coming back to the topic of the first lecture, how escape rate and mixing time are related. Before you have a chance to escape, so when you're confined to a ball that's smaller than the whole space, obviously you can't mix. But even when you go to far enough in the graph, that is no guarantee of mixing. And in the random graph, indeed, even when you get to the right distance, to the diameter, you're still not mixed. But the statistics that tells you that you're not mixed is quite sophisticated. It is, you have to look, when you're at the diameter, there is essentially a unique path to your starting point. And it turns out that path has atypical degree statistics. So if you ask along that path, how many vertices do I have of degree 1, degree 2, say degree 2, 3, 4, I still don't have the typical degree statistics along that path. And I have to wait for longer to develop typical degree statistics. So this kind of difficulty is hard to pin down. And so this is the result I mentioned earlier, cut off from a typical starting point. And again, what we use in the analysis is precise knowledge on the harmonic measure. So here is some picture of random walk on a Galton-Watson tree and the non-uniformity of the heating measure. So as I said, that is based on our work with Lyons and Pimentel from the 90s, where we showed the dimension drop for the random walk on the Galton-Watson tree. And so to analyze random walk on the random graph, there are several complications. One is that we have these vertices of degree 1 and the degree 2, which are harder to deal with. So in order to deal with them, we first consider random walk on a different kind of random graph, one where all the degrees are at least 3. So just like one can consider a random 3 regular graph, you can consider a random graph with given degree sequence. Say you want to run a graph with half the vertices degree 3 and half the vertices degree 4. You can do that by first just letting the vertices float in space, assigning each of n over 2 vertices degree 3 and n over 2 degree 4, and then doing a random matching. This is known as the so if I want to construct a graph with the given degree sequence, I just first put the n vertices with half edges. And so I put however many I need with degree 3, however many I need with degree 4. I need the total number of these to be even. And then you just do a random matching of these half edges to create your graph. So this is known as the configuration model. And it's a way to pick a random graph with given degree sequence. So the story I told you, reducing the random walk on the random graph to the tree, works nicely if all the degrees are 3 and higher. And the basic idea there is that the graph is well approximated by the tree for a very long time. So you can analyze the random walk by thinking of it as happening on the tree until you reach. So here is, the random tree, and the random graph actually has some additional edges that you don't see in the tree. But the question is, do these additional edges cause you trouble? So, of course, if you were to wait to visit the whole graph, you will see these additional edges. But if you wait only until your random walk would visit something like n to the 1 minus epsilon vertices, then till your the likely support of the distribution would be n to the 1 minus epsilon, then the random walk will not see these extra edges, and the approximation by the tree will be very good. And then once your distribution has been approximately uniform or approximately mixed on n to the 1 minus epsilon vertices, then you just switch to L2 considerations and you use the fact that your graph is an expander. So a random graph with degrees bounded below by 3 is with high probability an expander. And then you can use this expansion to go the rest of the way from being uniform on n to the 1 minus epsilon to uniform on n will only take time, which is order epsilon log n, which is good enough. So this is a very rough sketch for the case when the degrees are high. And this we knew a couple of years ago, but we were stuck on what to do on the Erdős-Renyi random graph, because there we have the leaves. So the leaves you can get rid of, but really the trouble is when on the tree when you have this degree 2. So this corresponds to even in the tree approximation, you have these long paths. And they certainly happen in the graph. Why do these long paths cause trouble? Because they ruin the expansion property. So you have long paths of length log n, so it means your graph is no longer an expander, and this is too far from an expander to work with the consideration I told you before. So the way to resolve that is to observe that even though in your path, in your graph, you have these paths of length log n, the random walk started at a typical point will not see them. The random walk only runs for log n steps. So it turns out the longest of these paths the random walk will see in its trajectory is log n. So what we do in the argument is we take all the paths in the graph of length bigger than log n, and we contract them to length log n. If you do that, you will get something which is not exactly an expander, but close enough to an expander that the previous analysis goes through. And then we have a coupling argument saying that the random walk on the real Erdős-Renyi random graph cannot see the difference between that and this kind of caricature we created by contracting these paths. So that is the idea. There's additional difficulties, but luckily there's a lot of work on random walk on Galton-Watson trees, starting from Grimmett-Kesten 84, my own work with Lyons P. Mantle and Dembo, Gantert, and Zeytouni, and just by applying generous doses of those previous works, we could overcome these difficulties. And let me stop here. Thanks for your attention.